Hi guys, welcome back to my channel. My name is Ciara Jessica Giron if you are new here. I'm a graduate of UCLA's Molecular, Cellular and Developmental Biology major, and I'm also a practicing software engineer. I'm a schizophrenic and I'm currently confined to government housing, and I'm working on YouTube to fund my exit out of the mental health system. Now that you and I know each other, I'm here with my third segment of my nervous system series, and this lecture will be based on the OpenStax textbook chapter 12.4, The Action Potential. As always, I have included a link down in the description box for new students to register with my QuickSchool program. If you are registered as a QuickSchool student with my program, you will have full access to all of my study materials, which include PowerPoint presentation slides and Google Doc notes, which I reference for these educational videos. My student package also includes personalized tests that I have created myself. Alright, now that all our intros are done, let's get into it. So what did we learn in our last lecture? In my last lecture, we talked about the different structural features of a neuron and about what kinds of different neurons exist. We learned about glial cells, how glial cells provide effective support for neurons, and where each glial cell is found within the nervous system. Some vocabulary words such as axon hillock and myelin will be great vocabulary words to study before getting into today's lecture material. What are we going to learn in today's lecture? In today's lecture, we will be covering a topic that is called electrophysiology. Electrophysiology is a subject which describes the conditions that establish resting membrane potential in neurons, and this subject also describes the behavior of electrical impulses that flow through neurons. Electrophysiology is actually one of my favorite subjects to talk about in biology for 3 reasons. 1, it is a challenging topic to talk about. 2, I get to have exciting conversations with other scientists about electrophysiology. And 3, electrophysiology is biology and physics mixed together. For the future, in order for us to understand how the functions of sensation, integration, and response are facilitated throughout the nervous system, we must first understand how neurons communicate with each other through action potentials. How are cell membranes electrically active, or in another word, excitable? Electrical charge can be built across a cell membrane by differences in proportions of ions, also known as charged particles, in the inside of the cell and outside of the cell. The ions that are of interest for today's lecture are Na+ and K+, which are otherwise known as sodium and potassium respectively. In this diagram of the cell membrane, which is called the fluid mosaic model, study the cell chapter if this is new to you, you can see that there are different proteins that are present within the cell membrane that are called transmembrane proteins or channel proteins. If you didn't know this already, the cell membrane is responsible for filtering out what comes in and what comes out of the cell. Ions are said to be hydrophilic, also known as water-loving, meaning that ions are charged and compatible with water. If this information is new to you, I would suggest studying the biochemistry of ions within biological systems. Ions can only pass through the cell membrane through transmembrane proteins. Pop quiz. Why do hydrophilic ions need to be transported across cell membranes using transmembrane proteins? You can see in the description below for the answer to today's pop quiz. This passage of ions is necessary in order to build a difference in electrical charge across the cell membrane. We will be looking at a specific channel protein that moves sodium ions out of a cell and potassium ions into a cell. This channel is a sodium-potassium pump that creates a concentration gradient. How does the sodium-potassium channel produce a gradient? The sodium-potassium pump creates a concentration gradient by actively pumping sodium ions outside of the cell and actively pumping potassium ions into the cell. Because the sodium concentration outside of the cell is greater than inside, and the concentration of potassium inside the cell is greater than the outside, those ions are being pushed against their natural concentration movements. This channel achieves this feat by harnessing the energy produced when the transmembrane protein acts as an ATPase. Transmembrane protein channels can be said to be gated, meaning that those channels require activation events in order for those channels to be opened. There are 4 different channels that I will be discussing in today's lecture: ligand-gated, mechanically gated, voltage-gated, and leakage channels. Let's look at a ligand-gated channel. Ligand-gated channels open when fitting ligands, also known as neurotransmitters, physically bind the extracellular region of a protein channel. You can see that when the red triangle neurotransmitters fit into the channel, the calcium ions can open the channel and allow sodium and potassium ions to move across the membrane. Mechanically gated channel. Mechanically gated channels open by a physical distortion of the cell membrane. For example, when a touch receptor is activated by pressure on skin, physical sensation is felt because a mechanically gated channel opens in response to the pressure. Voltage-gated channels. A voltage-gated channel is opened in response to a change in electrical charge, otherwise known as voltage across a membrane. For example, the cytosol inside a cell is usually negatively charged. If this cytosol becomes too positively charged, then the voltage-gated channel opens. Leakage channels. Leakage channels randomly open and close to maintain resting transmembrane voltage, or also known as resting membrane potential. Let's talk about resting membrane potential. Resting membrane potential is a fancy way of describing the electrical differences between the intracellular and extracellular environments of a cell. See this illustration. If the environment outside a cell was 20 millivolts and the environment inside the cell was negative 10 millivolts, the voltage across the membrane would be negative 30 millivolts inside the cell relative to outside the cell. It is agreed by scientists that the resting membrane potential of a typical cell is negative 70 millivolts. And now for the main event, I am introducing the action potential. An electrical signal, also known as an action potential or electrical impulse, is stimulated whenever there is a dramatic change in the resting membrane potential. When an action potential is generated, sodium channels open to admit sodium ions into the intracellular fluid. The sodium ions rush into the cell because the concentration of sodium ions is greater outside the cell than inside the cell. Therefore, the ions are following the concentration gradient into the cell. This event causes rapid depolarization of the membrane. Depolarization means that the voltage across the cell membrane is ascending towards zero or becoming more balanced. This graph illustrates how voltage across a cell membrane changes over time and is a visual representation of an action potential. Because the concentration of sodium is 10 times more outside the cell than inside the cell, the concentration gradient propels the membrane potential past zero to plus 30 millivolts, as you can see in this graph. In other words, the intracellular fluid is becoming more positively charged. The concentration gradient of potassium moves in the opposite direction of sodium, as the concentration of potassium outside of a cell is less than the concentration of that ion inside of a cell. Due to this concentration gradient, potassium ions leave the cell through potassium channels and repolarize the cell's membrane by reestablishing resting membrane potential at negative 70 millivolts. Peep the hyperpolarization dip in the action potential graph. Potassium channels are slow to close during repolarization. This means that extra potassium ions are lost from the intracellular fluid, and this results in a hyperpolarization. In total, the overall change in the cell membrane's voltage can be said to be 100 millivolts or 0.1 volts. This electrical activity that happens across cellular membranes is what the nervous tissue generates for communication. While on the topic of sodium and potassium exchange over cell membranes, did you know that sodium and potassium are essential electrolytes that are found within Gatorade and Powerade?
Please sponsor me.
Drinking these electrolytes after physical activity replenishes the ions in your body that are lost through sweating, and elevates your health by enhancing the electrical activity that happens within your nervous system, i.e., improving brain functioning and improving your reflexes. Let's get back to the content. How do action potentials get initiated? Let's think back to the different types of sodium channels that exist. A ligand-gated sodium channel opens when a neurotransmitter binds to it. A mechanically gated sodium channel opens when a physical disruption causes that channel to open. There are passive, randomly opening, leakage sodium channels that maintain resting potential. A voltage-gated sodium channel instigates an action potential when the resting membrane potential reaches negative 55 millivolts, and this voltage can be said to be a threshold. You can see this threshold at the purple line of the action potential graph. Some stimuli might initiate action potentials faster than other stimuli. However, all action potentials are all or nothing events. All or nothing in this context means that an action potential is only initiated if that voltage across the cell membrane reaches threshold. Otherwise, no action potential is actually observed. Also, there are no action potentials that reach membrane potentials over plus 30 millivolts, regardless of the strength of any stimulus. Now let's talk about the gate activity of sodium and potassium channels. Voltage-gated sodium channels have two gates, an activation gate and an inactivation gate. At resting state, the activation gate is closed and the inactivation gate is open. Once the threshold at negative 55 millivolts is reached, the activation gate opens, allowing sodium ions to rush in. The inactivation gate, which is a timed gate, closes after less than a millisecond at the peak of depolarization, preventing any more sodium ions from entering the cell, therefore allowing the system to repolarize. Can you start another action potential after one action potential occurs? The answer to this question is dependent on the conditions of the original action potential as well as the strength of the next stimulus. See this diagram to understand absolute and relative refractory periods. If the original action potential is in the absolute refractory period, then another action potential will not initiate. If an action potential is in a relative refractory period, then another action potential may be generated by a stimulus that is greater than the original stimulus. How is an action potential propagated through a neuron's axon? First and foremost, propagated means to spread widely, and in this context, the effects of an action potential spreads down a neuron cell's membrane, specifically down the membrane of the neuron's axon. Once an action potential is initiated, depolarization continues down the axon's membrane as more sodium channels open. Because sodium channels are prevented from opening again immediately due to absolute refractory periods, propagated electrical signals never travel backwards and only travel down towards the axon terminals. This phenomenon is referred to as cell polarity, which is what I talked about in my last lecture, 12.2 Nervous Tissue. Did you know that propagation occurs differently for unmyelinated versus myelinated axons? Unmyelinated axons of neurons produce slower propagations of electrical signals, while myelinated axons of neurons produce faster propagations of electrical signals. Electrical signaling involving myelinated axons is referred to as saltatory conduction. Saltatory conduction refers to the way that electrical impulses travel down myelinated axons faster than unmyelinated axons, because depolarization travels down a wider axon faster than it does down a narrow one. You can visualize the speed with which an electrical impulse travels through an axon by comparing a river to a stream. A myelinated axon conducts electrical impulses at the speed of a fast-paced river, while an unmyelinated axon conducts impulses at the speed of a slow-paced stream. Now that we've reached the end of this video, I just want to congratulate you for being a superstar for finishing this video. Electrophysiology is definitely not for the faint of heart, and understanding something as complex as electrophysiology is rewarding in itself. In summary, we learned that voltage differences across the cell membrane can be affected by ion concentrations, as well as the activity of transmembrane proteins, both active and passive. Finally, we talked about myelination and how myelination affects the speed with which electrical impulses travel down axons. For the next lecture, we will learn more about how interneuronal communication occurs by studying neurotransmitter release and reception. As always, I'm going to give a plug for my QuickSchool program. Solidify your knowledge by registering with me as one of my students, and take one of my tests if you're curious to see how well you know your stuff on this information. If you haven't already, hit that like and subscribe button to let me know that you want to see more of my educational content. Thank you so much for watching. I hope to see you in the next video. Bye.